Hello everyone, my name is Vaclav and I'm from Czech Republic, and today I will be presenting my work on behalf, or the work that I did with Matyáš Boháček, which is undergraduate student at Stanford and now researcher at Google DeepMind, and I am at Czech Technical High School right now in my senior year. My talk will be on controllable generation of synthetic video data for human motion. So as we all know, language and vision models progress in recent years mainly was boosted by large-scale, diverse, and in recent year, synthetic data. But human video data sets for action recognition or sign language translation or all of the tasks that require human to be in the video are not very diverse, large-scale, or if they are usually internet scraped, so they are not very clean, sometimes multiple people occurring in a single video. This is a screenshot from a dataset called NDU RGB, which, as you can see, is just in one room, like 4 people, so the model then doesn't generalize really well. So, and for sign language or action recognition or simple like driver monitoring, we need, the real data are very scarce or costly to make and sometimes even privacy constrained. You might think that we can use models such as text-to-video like Sora or VO3, which are photorealistic and today super fast also, but there is no hard pose control. And also the problem is that the models, as Andrej Karpathy said in his podcast, like LLMs also live on very small manifold. So when you say, for example, jump, all of the people in the generated video will jump in the same way, which is not very good for the action recognition model because they will not generalize to different type of like actions. And also prior synthetic data generation methods like ElderSim or Surreact were using like classical CGI or simulation methods, which are not very realistic. They don't have identity transfer. They cannot be very diverse because you need to hard code program the structure of the identity, and thus you cannot scale it. But the solution that we came up with is you create synthetic videos using post-transfer on the data set. So we extend the data set on new identities with new background. So just so all of us are on the same page, we can ask ourselves, what is post-transfer? So post-transfer is something that you have reference identity, which can be picture of human, video of some human. Today it can be generated by diffusion model. And then you have some type of novel pose, which can be from the data set, some person performing some action. And then we can reenact the identity on the image, or in our case, video. So first, we had to evaluate what type of post-transfer methods we have to do. We can use, mainly. So there are 2 types, generative methods or 3D grounded methods, or hybrids in between. So we came up with human evaluation task, which have 3 parts. First is semantics, where you basically ask what action is shown in the video, and people answer, and then you compute the correct percentage if people guess the right choice. Then you have consistency, which was simple yes/no question. How consistent is this motion? And then qualitative, where people simply yes or like adjusted the accuracy of the motion, if it's correct or not, if there are some random moves or physical constraints that are not real. So then the task was very simple. We have the driving pose, which is like person performing golf, for example. And then using diffusion model, we generated the target identity. And then using at the time state-of-the-art methods for post-transfer, which was animate anyone, magic animate, and xavatar. So animate anyone is basically diffusion model learned or trained with skeleton control, where we extract skeleton from the driving video, and then we try to diffuse a person. Then we try to diffuse the target identity. Magic animate is using depth control and dense pose control, and xavatar is using 3D Gaussian splats to have like 3D grounded identity that we can then animate. So here are some like qualitative results. So as we can see, magic animate doesn't perform really well. It performs really well on the benchmarks or control videos, but most of the data sets are not very clean, as I said. Sometimes there are multiple people, or the person is not centered, or there is some mask on the face of the person and model doesn't register it very well. Or animate anyone, which is a little bit better, but still there's a lot of physical inconsistencies. And then there's the xavatar, which have 3D grounding, but is still performing diffusion, but on the 3D Gaussian. So here, from the participant study, we found that xavatar has the best semantic results, also best consistency results, and also consistency results. And here are a few examples. So people found on your left, people found them consistent and inconsistent on the right. The same for animate anyone. And the same examples for xavatar, where even for xavatar there are a lot of mistakes made by the model. And qualitative, some people, mainly with all the diffusion models, such as magic animate or animate anyone, pointed that there are distorted faces, another person appeared there, or they are not photorealistic. So what is the main goal of the method for synthetic data? We want post-transfer quality, which using our human eval, we found that that's xavatar currently as a state-of-the-art for post-transfer. Then we want identity diversity, which is as many identities as we can, so the model can generalize to different ethnical groups, etc. And then scene diversity, which is backgrounds, because all the data sets are recorded in the same room, basically. So also we found that generative models provide realism, but lack control. Simulation engines offer control, but lack the realism. And xavatar, which is combination of both, has the best. It's not perfect, but it has the best results. So to create the diversity in identities, we created a data set that we call random people, which is 100 identities sourced from the internet. We paid people on the internet to basically record special videos, as you can see here, where for the xavatar to have the 3D identity, they need to perform certain actions, like do 360 rotations with raised arms, not raised arms. And we open source all of that as well on our Hugging Face. And so now the method for avatar creation. So first, the whole method, there are 3 steps. First is avatar creation. So we take the video, we subsample few frames, because we don't need, like, the videos are taken in like 20 FPS, and we don't need all 20 FPS per second, so we subsample it to 2 FPS. And then from each image, we basically extract SMPLX, which is like a 3D pose of the human. Then depth map, which is like a depth capture. Then key points, which is the skeleton. Then segmentation mask, facial expression, and also hand pose. So we have accurate hand gestures, and we combine all of this into single tensor, basically, and we call it body features. And then we train a neural network to correctly map the texture on 3D avatar of the person. Next, we have the reference video preparation, where we extract the pose of the person in the dataset video, basically, where we extract all the same information and have the body features, the body feature tensor as before. And then the whole combined method is where we reenact the trained identity on a new background and performing the action that the person in the reference video was doing. So this pipeline is much more that can create much more diverse and very easily, because you just need those sourced videos, then random background images from the internet and reference video from your dataset, and you can basically extend your dataset for human action recognition infinitely. Yeah, so then for some experimental setup to understand if those videos actually help the models. So we tested it on 2 datasets. One is NTU RGB plus D, and other is Toyota Smarthome. And Toyota Smarthome is basically elderly people performing daily tasks in their home. And we subsample 16 classes because we had to, our method yet doesn't take care of like multiple people in the scene or sometimes use of objects. So we had to clear for those classes that had all these like multiple people or objects. And per each data set, we generated 3,600 videos. And here are some results. Yeah, so the results are not perfect, but let's see if it helps the model, actually. But they can be physically consistent. Also, you can have as many identities as you want in any background. Many actions, it doesn't matter. It's generalizable, this method. And also there is a consistency where below is the synthetic video and above is the real video from which the synthetic video was created. So you can see that it's quite physically consistent. And so now some results. So because of computational constraints, because we are students, we took 225 real videos and 225 synthetic videos, and we trained two models. We trained 2 architectures. One is ResNet and one is slow fast, and then we tested on 50 real videos. And as you can see, sometimes there is 3 or 5-fold increase in performance in baseline experiments, where having just original was for Toyota around 20%, and for ResNet with synthetic and original was 50%, and for NTRGB there's even bigger increase. Then we performed 1 and few shot accuracy. So for 1 shot, which is basically you take 1 real video and then you increase the amount of synthetic videos, where you can see on the graphs or in the table that it still helps the synthetic videos, and the same is for NTU RGBD. And for few shot, which is where we take 5 real videos and then we add by 50, we add the synthetic videos and the curve grows. And if we would continue, we would get even better results after. So here are some limitations and ethics considering this project. So the framework has few limits, which is that it can do only single person in the video, and there is no interaction with objects to this date. And our current method sometimes can be scene displaced because the models are not big enough to have, but we can clear for those videos. And sometimes actions may be physically, like for example, if you would be cooking, but it would happen in a living room, then it's not very consistent with the real world. And all the research license is MIT, so it's open. And when we were collecting the identity videos, it was checked by Stanford people, and also there is demographic diversity to mitigate the bias in the data set that there's there to this date. And so to conclude, the contributions are, we have a toolkit for synthetic human action videos via post-transfer, and we can add backgrounds. It's very easy to use, very fast. And also, we have random people data set, which is 100 controllable identities that are released and open for research. And we have strong results on the Toyota, on two action recognition data sets, Toyota and NTU RGB. And if you have some questions, both of these work were presented at CVPR this year on synthetic data workshop, and the human evaluation was presented at face and gesture recognition conference this year. Thank you.
Thank you. Thanks for the presentation, first off. How are you seeing this as being applicable for like the ASL community, using that sign language? I know that you highlighted it lightly. How do you think we could get it to that accuracy to allow something like an AI translation service be used for them?
For sign language?
Yes.
So we did few experiments on that also. That was presented at Expo 2025 at Osaka this year. And we boost the results. And also the hand gestures can be very accurate if the videos are accurate, and most of the sign language videos are very accurate. So there is big potential because sign language datasets are very scarce. For American Sign Language, that's not a big problem, but for, like, for example, for Czech Sign Language from my country, or from other sign languages from like smaller countries, there are basically no data sets for them. So we can create synthetic data and possibly boost those results there also.